It was that bit.
Okay, let's start.
Right in my memory. Because I felt right on, like a song. Right in.
Okay, so this time hopefully my voice will last. I'll put the mic up. That's what I get for trying to teach with a cold. Do it all for you. But this time I brought my own throat lozenges. Thank you very much for last time. Hopefully I'll make it through this lecture and be able to speak all the way through. If not, I'll just flash the slides up in my notes. Okay? So we're switching now to planning, away from CSPs. CSPs, we're dealing with static situations where we simply have to find a set of values for a set of variables that satisfy a wide variety of constraints. Now we're dealing again with action. I mean, we dealt with action first in state space search, right? So we talked about A star when the action could go from one state to another state. But we're not going to go back to that. What we're going to do is use the advantage we gained in CSPs, namely breaking up the definition of a state into a set of features that have value. And by unpacking the notion of a state and giving it some internal description, we found that we were able to run things like arc consistency, which you couldn't do if states had no internal structure, if they were just atomic, undividable, right? So we're going to take the insights of dividing up states and representing them using features into the notion of planning, which we did with A star, but now we're going to do it in a more sophisticated way, and in a way which will scale up much more sensibly in terms of more complex domains. So that's the basic idea of what we're going to do in planning. We're not going to spend a lot of time in planning, and we're going to look at the strip system. We'll also look at the CSP representation of planning, so you can actually do dynamic action generation in CSPs, as we'll see how to do that. We use all the old CSP algorithms. So it's kind of nice closing the circle. Let me just remind you about a couple of things. You know, your assignment is due this Friday. I hope to get your assignment 3 out by this Friday as well. So you have something to keep you busy next week. And the midterm will be the week after midterm. So as I said, there'll be a lot of short answer questions, and I will, hopefully tomorrow, I'll put up a set of questions which I will choose from for this set, without answers, so you've got to figure out the answers to all of them. And then there'll be one long answer question. This will be rough weighting and so on. And I'll also put up a very similar midterm from previous instantiation of the course with solutions. And I will be away the week after reading week, unfortunately. I have a prior commitment. So Giuseppe has agreed to, Giuseppe Carinini, who's experienced and natural language human-computer interface expert, will be teaching for that week, those 3 lectures. I've asked him to make the slides available as I do. They may not go on the website, because I can only edit the website, and I won't have access. But he will either put them up on his website, or I'll get the TAs to put them in Connect, and you can see them there, and then I'll put them back on the site when I get back. Finally, I'm leaning heavily on the TAs to get your assignment 2 marked by Friday. Right, Cleon? Is that going to happen? Good. Glad to hear that. Students will be glad to hear it, too. Sorry, your assignment 1 marked by the time you get assignment 2. I think those are all reminders and logistics things. Are there any questions or anything before we delve into the content? Okay. Just one point. I put this in the Connect, so I thought I'd flag it here. We're going to talk a little bit more about Watson and Siri, because they're making a lot of news recently. Then we'll recap the last lecture again, briefly. And then we'll talk about intro to planning and examples, and then feature-based to the code. We're going to talk about feature-based representations, just as we did in CSPs. And STRIPS is a famous planning system, Stanford Research Institute planning system, problem-solving system is what it stands for. And it's been around since the 60s. It's amazing, and it's still used. And then we'll talk about planning a search, if we have time for that today. I don't know how we'll do. Okay, so let's talk briefly about Watson and Siri. And there's just a couple of links here you should be able to click on. That should work. That finger. So there's, of course I don't have, yeah, okay, there it is. This is a fairly good story here. There's a lot of stories in the media on Watson because IBM is now rolling it out as a product, primarily, as I said, for cancer, both for doctors and for patients, two separate products in local health clinics as well as oncologists. Kind of cool. They are planning to really exploit it heavily. Interesting. Thomas J. Watson founded IBM. He said if God had intended us to make intelligent computers, he would have told us that. And so IBM for decades refused to have anything to do with artificial intelligence. But once it got close to the market, they're smart. They picked up on it. They founded a whole division to develop Watson, primarily through Jeopardy, which is great marketing, and then into products as described there. And I mentioned Siri came out of a DARPA project, the PAL project, personal assistant that learns. The idea was to build actually sort of a secretary, admin assistant kind of person in business originally, and then more of a personal assistant with hundreds of person years involved in building it. And then they started a company which spun out of SRI, which is where STRIPS came from as well, Stanford Research Institute. Project run by Ray Perot. And that company was then bought by Apple, and then they put thousands of person years into developing it, giving it a much larger knowledge base, making it more robust, et cetera, et cetera. And it gets pretty good reviews. But one of the really interesting things is that if Apple does come out with this sort of Dick Tracy watch, which may be the next big thing, if it's not the ITV, then you've got a problem with a watch, right? Where do you put all the buttons and controls and menus and everything else? It's too small. So you talk to it. There'll be maybe only one or two buttons on the watch. And so Siri will allow you to make menu choices as well as ask it questions, and it will remind you to do things, and so on and so forth. The huge problem involved in both of these systems is question answering, which is, I talked about how that it's AI complete. You have to know all of AI in order to solve question answering. Every single aspect of that cycle between the environment, through the agent, through reasoning, and action back to the environment, right? So, and one of the central problems, of course, is uncertainty. How do you deal with uncertainty, both at the speech level, at the parsing level, and the knowledge representation level, and the environment representation level? You've got uncertainty everywhere. And that's what makes it so hard and why it's taken so long. But lots of breakthroughs in uncertainty management, which we're going to look at in this course, including Bayes nets and Markov decision processes, allow us to deal with this uncertainty efficiently. We knew how to deal with it when you basic probability theory, whether classical probability theory or Bayesian probability theory, but we didn't know how to compute with it efficiently. So some of those breakthroughs, which we will look at in the last two modules of this course, enable things like Watson and Siri to achieve what they've achieved. And one of the most important things is sort of this meta-knowledge about how confident are you in your own answers, right? In Jeopardy, you have to figure out how much to bet on your answer, right? So if you're not that certain, I think one of the screw-ups in the final Jeopardy competition was that Watson said that Toronto was an American airport. But it had lots of question marks after it. It was the lowest, it would have very low confidence, but it was actually greater than all the other ones you could think of. But that got it some bad press. But this idea of knowing about your own reasoning, meta-reasoning, and in particular knowing how certain you are in your answers is obviously really important for any kind of trust from the user to the system. And trust and credibility are key issues for any AI system. But they seem to have got some good answers in both IBM and Apple. And there's lots of, obviously, huge, inconceivably large number of applications of this kind of technology. So let's quickly recap stochastic local search. First, I just we didn't really talk about plateaus, and actually they're one of the biggest problems in search. You don't see them so much in small search problems, like when you've got 1 or 2 dimensions, but when you've got 1,000-dimensional spaces, you find very large regions of the space which are just kind of flat. There's not much information about where to go. There's no local knowledge about which direction to go to get a much better solution. So first, we defined the idea of a minimum, and there are 2 kinds of minimum. There's sort of a strict local minimum, where any change will improve the heuristic. If you're trying to, if you're trying to decrease in this case, we're minimizing, not maximizing. So if you get to a strict local minimum, then any change will increase it, and so you know that is absolutely the best local position. But often you get this kind of plateau at the bottom of the minimum, so you may go in some direction. It might be a while before you increase it. So right here, you wouldn't be able to tell locally if you were at a minimum. But what's also very common is this idea of a plateau, which you can have various kinds. You could have a plateau which is next to a minimum region, and then it goes up, or you could have a plateau where you could go down on the other side. And so these are very common in very high-dimensional spaces. Some problem instances have very large plateaus in high-dimensional spaces. And so we need ways to search them effectively. So one of the motivations for all these different kinds of stochastic local search algorithms we had was that they can actually do very well at not only escaping local minima, we talked about that, but also about escaping plateaus. Right, one of the problems with the plateau is you might just sort of wander around aimlessly around the plateau and never explore off the edge. So for example, if you use taboo search, you can never backtrack to where you can never go back to a previous search position in the space for at least k moves, where k is some variable parameter for the taboo search. The genetic algorithms allows you to take 2 positions in the space, cross-combine them, and jump into 2 other perhaps completely different positions, jumping off that plateau, and so on and so forth. So that's one of the motivations for all these different variations of stochastic local search. But the price you pay for those things is you have a large number of parameters, right? Typically. We looked at some of those. So then we talked about this idea of automatic algorithm configuration, which is, in a sense, applying stochastic local search to itself. This is, again, this kind of meta-knowledge we were talking about. You're searching over a space of possible algorithms, and each algorithm is doing a local search. Right? So you have some set of instances that you want this thing to work on. There may be just not all the instances you're going to work on, but some sort of training set, 10%, or some well-sampled set of instances you want to solve. You run the algorithm on it with a set of parameters. You change the parameters, it gets different performance. So that performance is a heuristic measure that you're trying to minimize, right? If it's time or space or whatever. So this idea of automated algorithm configuration, which a lot of the work has been done here, is trying to optimize this performance of these arbitrarily parameterized algorithms. And by parameter, you might just think, well, this is a number, it's like an integer or a real. But you can have categorical parameters, where they're categories, They could be just a finite set of alternatives. They don't necessarily have any ordering, right? So you can't search using the ordering in the space. For example, you might consider you're running different versions of A star. Each one uses a different heuristic, right? You want to figure out which one is the most effective on this class of problems you're trying to solve. Different ways of different data structures inside the search algorithm. Different Java classes, if you have kind of a framework implementation, which you can swap in and out Java classes. So this idea of automated algorithm configuration is fairly powerful. And as I say, if you look at Param ILS, which was working on essentially solving linear programming problems or integer programming problems, then this is a pretty powerful way of doing it, and it's getting orders of magnitude improvement over the state of the art, okay, using AI techniques. So again, very relevant stuff. Okay, so we're going to talk briefly about an intro to planning, and then talk about an example. So just where we are in the course, we've done this, constraint satisfaction. We talked about the representation. Remember, this is the representation, variables plus constraints, instead of using states, where features and variables are interchangeably used here. And two different inference techniques, ways of finding satisfying assignments, either using direct search or using R consistency plus domain splitting in search. Okay? There are alternative ways of solving CSPs. We've done all that. So now we're going down here to planning. We're going to talk about, really only talk about one representation, the strips representation. The book talks about another one, and I'll mention it briefly, but we're not going to look at it in detail. And there are two ways of solving these kinds of strips represented planning problems, again using standard search, which is pervasive, of course, or, as I mentioned, we could use CSPs to actually solve planning problems using our consistency. So that'll be interesting. So, I really just said this before. With CSPs, we're looking for solutions that are atemporal, that is not temporal, static problems. We just want to find a single state or variable assignment that satisfies all the constraints. We don't care about how we get there, how we search to find that, as in distinction with the A* search routines where we actually care about the path. You don't care about the path in solving a CSP using search. So we've got different kinds of problems now. These are temporal problems where you're given a description of an initial state, not just the name of the state as you would be in A*, and a description of the effects and preconditions of actions. So in order to do an action, the world has to be in a certain configuration or set of configurations where it's only applicable there. You know, if I want to pick up something on the table, A, my hand has to be empty, B, the thing has to be there on the table, B, C, I have to be able to reach it. Those are preconditioned to actions, and once I picked it up, it'll no longer be in the table, it'll be in my hand. And my hand will no longer be empty, it'll be holding the cup, so on and so forth, right? Those are the kinds of things we'll be dealing with. And we want a goal to achieve. It might be drinking coffee in my case, but you know, I have a set of preconditions. In order to drink coffee, the cup has to have coffee in it, it has to be at my lips. How do I get the cup at my lips? Well, I have to look for a cup, find it, pick it up, take it to my lips, etc. Right? So there may be goals and sub-goals. In order to set up the preconditions of an action, you may have to solve a sub-goal, which has preconditions recursively on back until I get to the initial state of the world, say, oh yeah, I could solve that. And then you go forward. So I can solve these kinds of problems by that kind of backward search from the goal, saying, here's a goal. What actions do I know how to achieve that? Okay, well, they have preconditions. Are they true? No, if they're not true, I have to make them true. How do I make them true? Reason backwards until you get to the initial state. Or I could reason forward from the initial state. What states can I reach from the current state of the world? Everything I could think of, everything I could do till eventually I'm drinking coffee, right? So that would be. So there are obviously at least two ways to solve these problems, forwards and backwards. We're going to look at forward search initially. So we want to find a sequence of actions that's possible and will result in a state satisfying the goal. Okay? So again, unlike the CSPs, we're just interested in a single state. You want a sequence of states that gets us to a goal, but these states will have structure. They'll be described. So this is the key idea of planning. We're going to open up the representation of states, goals, and actions. Each of these will have some internal structure, and we're going to use features to represent that internal structure. Okay? So states and goals will have features, or as I say, feature, variable, we use them interchangeably, variable assignments, as in a CSP, and actions will have preconditions and effects defined on those features. Okay, so in order to represent a planning problem, you have to decide what are the features, what values can they have, what are their domains, and so on. And so now the agent can reason more deliberately about what actions to consider to achieve its goals. As I said, if I want to drink coffee and precondition of drinking is the cup is at my mouth and it has the right liquid in it. But those preconditions, in order for that to be true, there are certain other actions I must have to take. But I'm describing those individually. I don't care about where the rest of you are when I'm thinking about drinking coffee. I don't have to describe the entire state of this classroom. Right? I just have to describe the things that are relevant to my actions and the goals I want to achieve. I can assume the rest doesn't affect it. So you get an enormous gain in efficiency of representation by doing this. Okay, so let's think about comparing this to simple graph search. In graph search, we had states, start states, goal states, and a successor function. Right? A successor function just took any state and would tell me whether or not I could reach other states, and if so, what they are, what set of states that could be produced from this start state. Okay, when you apply an action in state S, you end up in S prime or some set of S primes. We can consider that a flat representation. Okay, all the states have equal status. There's no sense in which I could say state 1 is close to state 6, right? The state of this classroom is no different, or is no closer or different than the state of any other classroom or the state of Mars, as far as the state-based representation is concerned. They're all just different states of the universe. Okay, no sense in which we can say that one is closer to another. They're just nodes in the graph. And so the only way to represent the successor function is really just as a table, right? For each starting state, through the successor function, you can end up in a resulting state. Okay, it's sort of an explicit tabular representation. And of course, for simple problems, you can get away with that, but as soon as the state, as soon as the world gets interesting, the robot is dealing with many different rooms, many different coffee cups, whatever, many different people, that will just explode. Every time you get a new object in the world, you multiply the number of states by the number of values, the features, that object could have, right? Just explode exponentially every time you add a new object. We've already seen that kind of explosion, right? So we need to deal with that combinatorial explosion. But another problem is that very small changes to the model could mean big changes to the representation, right? If you just add another variable to the description you're interested in, like I might be just dealing with cups and tables and everything else, and suddenly I'm deciding I'm interested in what's inside the cups, right? My state-based representation, everything will change. All my states would be multiplied by the kinds of things you can have in cups, so on and so forth. If we're dealing with the kind of feature-based representation, we just say there's another feature, the contents of a cup, and it can be liquid or solid, or it could be milk, coffee, water, whatever. That's all. It's much more modular to change the representation. So we'll get structure and regularity to the states, to the actions, and we just can't capture that with a tabular representation. So it's not just the exponential explosion that we're worried about. And we've already seen this by using features in CSPs to show how a feature-based representation is much more compact than a state-based representation of the same problem. If you take the state-based representation, you have to sort of multiply out the feature-based. You multiply the size of each domain to get the size of the state space that you're dealing with. But in CSPs, we didn't ever when we're solving them, we don't explicitly represent the state space. Right? For each variable, we just have the set of values it could have. We don't multiply them together. That would guarantee it would be an exponential blow-up. We didn't want to do that. We just ran things like arc consistency, which was very efficient on this small representation. Okay, and the reason for that is that because we factored states into joint variable assignments, each constraint only mentioned the variables it constrains, would allow efficient constraint propagation. You can't do that in a flat representation. So we're going to try and do that in planning. That's the idea, right? So it's easier just to do an example to get a more concrete sense of what's going on. So this is straight out of the book. We've got this robot called Rob, and Rob can visit 4 different spaces, and it can go either clockwise or anti-clockwise, counterclockwise. Okay, and Rob can do the following things. It can pick up coffee, it can deliver coffee, it can pick up mail, and can deliver mail, right? And there's a human in this world called Sam, but Sam is stuck in this office, can't go anywhere. But occasionally, all he's doing is proving theorems over and over again. Mathematician. So, and we know a mathematician is a machine for turning coffee into theorems. Right? So when he runs out of coffee, he stops producing it. So he calls the robot on his iPhone, and the robot says, hang on, I'm just delivering mail, but I'll get back to you, and runs off and gets coffee if it doesn't have it. Better be warm by the time it gets to Sam. That's the kind of scenario. Okay? So these are the features for the states in this problem. The features, again, we're going to use uppercase to represent variables that have values. Okay, so rlock is Rob's location. RHC means robot has coffee. So this variable can have 4 different values. Rob can either be in the coffee shop, Sam's office, mailroom, or laboratory. So rlock can be equal to coffee shop or equal to Sam's office. The shorthand for rlock equals coffee shop is just CS, the coffee shop. So again, we use lowercase to say this variable, uppercase, has this value, lowercase. We'll just use the lowercase to indicate that rlock equals coffee shop, rlock equals Sam's office, and so on. Robot has coffee. This is a Boolean variable. So either he does or he doesn't. So we'll just use RHC, lowercase, to indicate that he's got coffee, and negate RHC with a bar across the top if he doesn't have coffee. Rather than saying RHC equals true, RHC equals false. That's all shorthand, right? Similarly, for Sam wants coffee, he's either thirsty or isn't. Mail's waiting in the mailroom, either it is or isn't. And robot either has the mail or he doesn't have mail. Okay? So those 5 variables describe the state of the world. So, for example, I have a vector now which gives the value for each of the 5 variables. The robot is in the lab. The robot does not have coffee. Sam wants coffee. There is no mail waiting, and the robot does have mail to deliver, presumably. Okay? So we've got a structured description of the state. It's a 5-tuple now, as opposed to just being a name, S33. It's a 5-tuple with these 5 different values. So how many states do we have in this world? Done this a few times. Get your cards out. Work out the answer. See if your neighbor has the same answer. If they don't, convince them. Or have them convince you.
Oh yeah. So one of them yeah, 4 locations. 4. Okay, so it's still our 6 then.
Okay, this should be almost second nature. Just whatever time it takes you to do the arithmetic should be the only time required to solve this problem. Right? I mean, this is a typical state, right?
Right.
So the number of states is the number of values you could have there times the number of values you could have there. These are all orthogonal conditions, right? Robot have mail doesn't depend on whether or not Sam wants coffee, etc., etc. They're orthogonal. It's not the case for every state space that these are independent, but here they're independent. So the number of values you could have there times the number of values you could have there, blah, 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 which is what? 64. Thank you. Okay? That should be, as I say, second nature, just multiply them together. But only if they're orthogonal, right? It's not always the case. So those are the possible states in the world. There are 64 of them. We're not going to want to multiply them all out, but we need to know how big a state space is. So I say the possible moves. He can move clockwise or move anti-clockwise. Clockwise or anti-clockwise. They can pick up coffee. He can always move clockwise or anti-clockwise. There's no precondition on that. Wherever he is, he just goes to the next one. But you can't pick up coffee anywhere. The only place you can get coffee is the coffee shop. So the location of Rob, it must be coffee shop in order for pick up coffee to work. Otherwise, it's not applicable, right? Its preconditions aren't satisfied. in order to deliver coffee. Rob has to be delivering it to Sam, who's desperately trying to prove another theorem. So Rob has to be at the office and must have coffee to deliver. To pick up mail, you must be in the mailroom, and mail must be waiting. To deliver mail, you must be at the office for Sam and have mail to deliver to him. Okay? So those are the preconditions for these actions. And this is very typical in this kind of problem, that there are very discrete conditions that must be true in the world. In order to deliver mail, you must have it. You must be in the right place, so on and so forth. If we could use a state-based representation, if we were dumb enough, we could list all 64 states, and for each of the, how many actions are there? 5 actions, 6 actions, because you can move clockwise or counterclockwise. There's 6 actions. So 6 times 64 would be the length of this table, right? For some of them, there's no resulting state because the conditions aren't satisfied. For others, there are resulting states. So I could write out that entire thing, and then I could use that as my successor generation function and use all the old state-based stuff. That would be a dumb idea, but it would work, okay? You need an entry for every state and every action. But better would be to use something like this, a more compact representation. To pick up coffee only changes a subset of the features. If you pick up coffee, it doesn't change whether you have the mail or not. You can do both, carry both at the same time, right? For example. So pick up coffee only changes robot has coffee. And it only depends on a subset of the features. It only depends on where he is. It doesn't depend if he has the mail, right? And you can't pick up coffee if you've already got coffee because you can't carry 2 coffees at once. So the precondition for pick up coffee is the location is the coffee shop, and robot had coffee is false. The effect is that he has coffee. Okay, so we'll do that for each one of them. Okay? Stop me with questions. Okay, so what we learned so far is that the state representation just doesn't scale. It's A, doesn't scale, and B, isn't robust against changes in the world, changes in the representation, adding features and so on. This might help. We haven't seen how yet. So how would it help? Well, we know how to do states. We've just done them with CSPs, but the key is in modeling actions. How are we going to model actions? Okay, this is the idea. There are 2 ways to model actions. Okay? We're going to look at both of them. You could model when the actions are possible in terms of the values of the features in the current state, or you could model, you have to do both of these. You have to model when the actions are possible in terms of the values, and model the state transitions in a, quote, factored way. That is, just explain or show what changes. Okay? And we've already said all this. Why is this more tractable and manageable than tabular? Depends. If you're only modifying a few features, that'll be more compact, exponentially more compact, and it's easier to modify and update. Okay, so let's say there are really 2 ways we're going to do this. And the book does both, and we're not going to focus on this first one, but it does talk about a feature, and it's like this dual idea we had in CSP representation. You can focus on the features. I have a feature-centric representation. For each feature, you can describe which actions affect it. Or you can focus on the actions and say, for each action, what does it do to the features? Okay, so you either focus on the features or the actions. There are arguments both ways. The most common way to do it is the action-centric, so that's the one we'll do. But if you're interested, you should look at this. But if you're going to use a feature-centric, you have to talk about causal rules, the way that you could change a feature's value by taking an action. But you also have to give frame rules that, frame specifies how you go from one state of the world to another state of the world. You have to specify for every single feature, how does it change? And if the actions change some features, you tell how they change it. But then you have to say for every other feature, it's unchanged. That's what we call a frame rule. That's sort of the non-side effects of an action, because otherwise you can't assume that they're going to be changed or unchanged. You have to specify that they're unchanged if no action changes it. We're going to do that within this strip representation. You're going to specify for every action what does it do. And the way we're going to state these frame rules about what happens is very simply, anything not explicitly changed by an action stays unchanged. Well, you might think that's obvious. I mean, of course that's the case. But it's not always the case. I mean, if I have a cup and a saucer here on the table, and I pick up the saucer and move it, the saucer moves, but also the cup moves. But the table doesn't move, right? So there's something I didn't mention. I didn't mention the cup in the moving the saucer action, but it actually had the side effect of changing it. So we're going to disallow that. So it's a very strong restriction that anything not explicitly changed by an action stays unchanged. And of course, the reason we make that is for computational efficiency. And all of these restrictions can be waived, and there's a whole stream of AI research for the last 3 decades called the situation calculus, developed by John McCarthy and Ray Ryder and Pat Hayes and various other people, which waive all of these restrictions. But we're going to, for simplicity, we're going to make these simplifying assumptions and see how far we can get. And we do know that this is going to be more efficient to go this way. So as I said, this STRIPS representation stands for the Stanford Research Institute Problem Solver, developed in the 60s by Rich Fikes, Nils Nilsson, and a few other smart people. This is really an amazing robot. It's in Washington, in the Science Museum. Because it was the first AI robot ever, the first cognitive robot that could actually reason about things and do things autonomously. This guy is called Shakey. I mean, that was, it was like running probably a PDP 3 or 2, like 32 kilobytes of memory, 1K instructions per second. Amazing computer for the time. But it also shook a lot. They had this tower, right? And it's got cameras on top, all sorts of cool stuff. It's amazing what they did. But it was a little unstable, so it would move and then shake. And there's some great demos. You should search the internet for this Shakey demo, where they show it solving a problem. They used to push blocks around and push things up ramps. So move the yellow block over in front of the green block. That would be the kind of thing it could do. And there's one demo where there's a clock on the wall, and it shows the command being given to Shakey. And then in the next frame, you see it executing the command, but you notice that the clock has jumped. I have to get into like half an hour or an hour or two between the first frame and the second frame. They did a few edits on the video. But, say there was very limited computational resources. But STRIPS was the planner inside Shakey doing all this reasoning. And in STRIPS, an action has 2 parts. It has the preconditions, which is a set of assignments to variable that must be satisfied in order for the action to be legal. And the effects, a set of assignments to variables that are caused by the action. Okay? So with our example here goes my voice. If we have the action pick up coffee, the precondition is this variable lock must have value CS, and this variable RHC must be false. And the effect is RHC equals RHC. The robot has coffee. If you deliver coffee, the location must be the office, and you must have coffee. The effect is you don't have coffee once you've delivered it, and Sam doesn't want coffee anymore. Notice that Sam doesn't want to have to want coffee for him to deliver it. He can deliver it, whether or not Sam wants coffee. If he didn't want coffee before, he still doesn't want coffee. But if he did want coffee and it's been delivered, he will drink the coffee and he will not want coffee. So there are 2 ways to get to Sam doesn't want coffee afterwards. Either way is true here. So we don't have to have a precondition here that Sam wants coffee in order for him to deliver. The robot doesn't care. He just comes in his office and dumps it down and says, here's a coffee, drink it. He doesn't want to drink it, that's his choice. Okay? And again, the STRIPS assumption that all values not explicitly changed by an action stay unchanged. Which is not true in general, but we're going to make it true. We can only work with worlds that's true. So if some feature V has value VI in state SI after action A, so we show that down here, we've performed this action A, we reinstate SI where B has the value BI. What can we back infer about A and or the state of the world, SI minus 1, this one, immediately preceding the execution of A? What are the preconditions? What can we say about this action or the state of this world? Those things together. Okay? That's the question for you. What can we conclude about A and or the state of the world, SI, immediately preceding the execution of A? Think about it. V equal VI was true in the previous state. One of the effects of A is to set it to true. At least one of the above is true. Both of the above is true. Think about the Sam wants coffee example previously. So all we know is that it's true here. So what can we conclude from that? Talk to your neighbor. See a lot of uncertainty here. Okay, time's up. Place your bets. Put up your card. Okay, some of you got convinced, a lot of you are convinced that it's at least one of the above, which is correct. Could both be true, but at least one of them has to be true. I mean, think about how this could get its value. It might be that A has nothing to do with this variable. It doesn't mention it. Okay, so the frame rule says because it doesn't mention it, if it's got its value here and it's not mentioned by the action, then it must have been true there. So that's one possibility. The other possibility is that A does affect the value of B and sets it to VI, regardless of what it was before. We don't know which of those is true, so we can't say that it was definitely true in the previous state. It might not have had that value and it was set. So that doesn't have to be true. This doesn't have to be true, but at least one of them's got to be true. Both of them could also be true. Does that make sense? That's really important to understand. If you don't understand that, you didn't understand the stuff about frame rules we just went through. Okay? So it's red, purple, or whatever that. Okay? Is there a question about that? So we're back inferring the preconditions on an action from its effect. So let's quickly look at forward planning. Say you can solve strips problems in two ways, either as a pure search problem, either a forward search or a backward search, or as a CSP problem. We're going to look at one technique for each approach. We're just going to look at forward planning here, and we'll look at a straightforward CSP version here. But you could do, as I said, you could do backward reasoning. Backward reasoning in this kind of representation is called means-ends analysis. Okay? We've got an end. We've got a goal we want to satisfy. We rack our brains and say, which of the things I could possibly do could make that goal be true? It's not true in the current world. I look through all my tools. It's like, I'm trying to unfreeze a bolt, say. How could I unfreeze a bolt? Well, I could use a wrench, or I could use some liquid wrench, etc. Or I could hit it with a hammer. Right? In order for each of those three actions, I'd have to look in my toolbox and say which ones I got, what their preconditions are. So reasoning backwards from the tools would solve the problem back to the initial state. Okay? We're not going to do that, but we could. We're going to do it forward for search. Okay? So we're going to search in the state space graph where now we're going to represent the nodes using these 5 tuples, or in general feature tuples, rather than just by their names. So the nodes represent the states. The arcs correspond to the actions. The arcs from a state represent all of the actions that are possible in a state. A plan is a path from the state representing the initial state to a state that satisfies the goal. Okay? So this is planning. We're producing a temporal plan. But you remember right back at the beginning, I talked about the omniscient robot, omniscient fortune teller assumption. This is in the omniscient fortune teller mode. We're saying that the robot knows everything about the current state it needs to know. For each of its actions, it has an internal model of an action. Here are its preconditions, here are its effects. Every time I do an action, it exactly does the right thing. When I pick up a coffee, I pick it up. When I go to the coffee shop, I can always get coffee. I never drop it or run out of money or my Starbucks card is empty. None of those failure conditions can occur, and so on and so forth. So once you've got a plan, the robot can execute it blind because it knows its internal model of the world will unravel the same way it actually happens in the real world. Nothing could possibly go wrong in this model, right? It's a very optimistic robot. So again, it's a good place to start. So what actions are possible in a state S? What actions A are possible in a state S? What do you think? Quickly, you should be able to get this one right away. So the arcs from a state represent all of the actions that are possible in a state. What actions are possible in a state? Those where A's effects are satisfied in S, those where the state S prime reached by A is on the way to a goal, or those where A's preconditions are satisfied. What do you think? Show me a card. What can I do in a goal? In any state? Yeah, the preconditions have to be satisfied. That's what they are. They're preconditions. They have to be true. In order to do an action, you have to check to make sure all its preconditions are true. Otherwise, you can't do it. They all have to be true. Okay? So, using that idea, we can start, suppose we're starting here where the robot's in the coffee shop. He doesn't have coffee. Sam wants coffee. There's mail waiting, and the robot doesn't have mail. And we want, this is the goal, not Sam wants coffee. So if that were true in the initial state, we just say done, we stop. But it's not. So we can see, you think about all the things you could do in this state. You check all the preconditions of all, 6, 7 actions. Only 3 of them have their preconditions satisfied. So you get 3 successors. And you know how to generate the successors. You check the preconditions. You look at the effects of the actions, and you put those in the new state. Okay, so if he picks up coffee, then you go from not robot have coffee to robot have coffee. Nothing else changes, right? Because of the frame rule, right? Etc. If you move clockwise, the only thing you change is the position of the robot from CS to office. If you go anti-clockwise, you go from CS to the mailroom, this way, and so on and so forth. Okay, so we'll stop there for now, and we'll pick this up again on Friday.